So Gaussian sub-exponential random variable is defined via its Bowman-Jennings function satisfying this inequality. And if you look at it closely, it's almost exactly the same as sub-Gaussianity, except that we don't require it to hold for all lambda, we just require it to hold for lambda close enough to 0. Okay, so if you think about this 1 over alpha, this is the radius over which this needs to hold. And so it's characterized by 2 parameters, nu and alpha. Nu is like the sigma squared that we have in sub-Gaussian. And alpha is some extra parameter. So if alpha is infinite, this is useless. If alpha is 0, it's just sub-Gaussianity. So generally, it's alpha between 0 and infinity. And so sub-Gaussianity is, or sub-Gaussian random variable is a exponential random variable. So sub-Gaussian class is a subclass or subset of sub-exponential class because it's obvious it holds for all lambda. It holds in the neighborhood of 0. So a general random variable is sub-exponential if the centered version is sub-exponential. Again, this inequality is for 0 mean random variables and it enforces the 0 mean. So whether the random variable is 0 mean satisfies this, it has to have 0 mean if you do a Taylor expansion of both sides. So a non-trivial example. So obviously, not obviously, but by the name, you might imagine that exponential random variables are sub-exponential. So the tail looks like exponential random variable. But a non-trivial interesting example is if you have a Gaussian, it's standard Gaussian, then z squared is sub-exponential. To show it, you can compute the, first it's not 0 mean, so we subtract the mean. So you need to apply this definition to the centered version. And then we calculate the NGF. The NGF happens to be finite if lambda is less than 1/2, infinite otherwise. And this is the result of the integrate. So we'll see later on that it's often just the fact that it's finite in the neighborhood of 0. NGF being finite in the neighborhood of 0 is good enough. That's sort of an alternate characterization. But you can also manipulate it using an inequality to show that this is bounded, for example, like this, if lambda is less than 1/4. So this is an exercise for you to do. That if lambda is less than 1/4, then you can bound it like that. So it satisfies this inequality. Parameters nu being 2 and alpha being 4. So it's sub-exponential parameters 2 and 4 at least. Again, nu and alpha are not unique, so you just have to show or provide one example. So this is all good. Let's say we agree with this. Can we say that z squared is sub-Gaussian? We know it's not the sub-exponential, but maybe it's even sub-Gaussian. Can we comment on that? Could it be sub? So I've shown that z squared is sub-exponential, but we know that the sub-Gaussian random variables are inside the class of sub-exponential. Maybe this is actually sub-Gaussian. We bet that yes.
No, because it has the whole for all lambda.
Okay, can you speak up?
No, because it needs the whole for all lambda.
It needs to hold. So this is an inequality that is right? Maybe it holds for all lambda. I don't know. I haven't specified what happens if lambda is the minimum. But here it is specified NGF for all lambda. Can you argue based on this? Yes, and this I can't argue because this is just between what it is, like near zero, maybe above, like above this threshold is also like that for some bigger, maybe like a case here, it would work out. But you can argue from this because I'm using the entire MGF here. You can argue that it's a Gaussian. We go back to the properties. We go back here. So I should remove the so you can already see, let's say, from this, the original characterization that this has to hold. Yeah, from the fact that this has to hold for all lambda from subgaussian, that this cannot be infinite for regular lambda. Right? So the fact that this is infinite for some lambda is enough to violate subgaussian. This also means that some of the moments do not exist. So, but it's enough. So the fact that it's infinite means that it cannot bound the radius beyond it. Yes, I'm not sure if it was like this, maybe you have to worry about. But once you see infinity here, so a random variable whose MGF is infinite at some point cannot be subgaussian. Okay, so this is a proper sub-exponential random variable. Sub-exponential, but not sub-Gaussian. Okay. Yeah. That's what I sort of was pointing out. So sub-exponential means the tails are below actually an exponential random variable. We'll see. So the tail at infinity. So for the Gaussian, for sub-Gaussians, we have this characterization that the tails for large extension for all t is like e to the negative t squared divided by something. So that's the way that this PDF or the tails actually. So the 1 minus the CDF, let's say, right? The CDF, 1 minus the CDF, the Gaussian decays. The same goes, we'll see, for sub-exponentials, the tails decay like e to the negative t to something rather than t squared. Other questions? Okay. Good. So we have one example. We'll see more. So assume that x is 0 means sub-exponential random variable satisfying 2. This is the counterpart of the proposition that we had for the sub-Gaussian case. So we have a tail down, looks a little bit more complicated. So it used to be like e to the negative t squared over 2 sigma squared. Now you can see the two regions basically. The tail, if you look at like this, what this is saying is, so which one is going to dominate for small t, which one is going to dominate for large t? Up to 2. So one of them would be active. Point. T large versus T small. Anyone? Right, which one? For large T. Yeah, so this is quadratic. Eventually, this is linear. It's ignoring the constants. Eventually, this is going to be smaller. So for large t, this is going to be the minimum. And so the tails, the large deviations are e to the negative 1/2 t or alpha. For a small enough t close to 0, the first one is dominant. This is because, like, you know, the way that like a quadratic starts very near zero, but then just jumps up. Linear functions are just like this. So at some point they cross. So near zero, this is the minimum. Above zero, the linear one is the minimum. And so do this. Let's say this is below there, so it would be like that, and then at some point jumps to linear. So this function looks like this, just up to some point where the other one is going to be the minimum. The other ones will process it. So that's how the tails behave. That's where the sub-exponential sort of idea comes in, because this is how, if you recall it, say if x is exponential an exponential random variable with rate lambda, what is the probability that x is bigger than t? You want to remember. Sorry. Yeah, okay, great. Negative lambda t, yeah. For t bigger than equal to 0. So this behaves like questions. So let's try to prove this. If you recall, this is on Chernoff bound, this holds generally. And then I'm just going to plug the bound that I have on the MGF, which is, this is the MGF, this is the bound that I have, like e to this. And then I want to minimize it. The only difference, after this point is exactly like the subjective. The only difference is that I can let lambda, so lambda can be just between 0 and 1 over alpha. Because I don't have the bound elsewhere. So it's the constraint optimization problem. Okay, so if you want to do it, I've defined this function, f lambda. So f lambda is just the exponent here. Again, we're going to do derivative as usual. You know that this has a minimum, just it's easy to do it like this. Minus t plus nu lambda squared equal to 0. So t has to be nu squared lambda equals 0. Lambda has to be t over nu squared, right? So this is the quadratic with positive second, let's say quadratic function with a positive coefficient for the quadratic term. And so this has a minimum. You know that there's a minimum, and it has the minimum is there if you're looking at everything over the entire real line. So at 0, this would yes, if you look at this, there is a root at 0, right? There's another root somewhere else, and then in between this has to be like this. So there's a root here. So if you look at it, there is a root at 0. There should be a root somewhere here, I believe. And then we have, should be symmetric. And this point is lambda equal t over nu squared. Okay. So the only thing that matters now is where 1 over alpha is. So if, for example, 1 over alpha is here, this is 1 over alpha, then in this interval 0 to 1 over alpha, I have the global minimum. So this, if it's here, for example, 1 minus alpha is less than this, then the minimum just occurs on 1 over alpha. So having the regime, And this is basically what we have here. So if t over nu squared is less than 1 over alpha, we have the global minimum, which is this. And if t over nu squared is bigger than 1 over alpha, we just hit the boundary, and then that would be the minimum. So you plug it in there, and if you believe my algebra, they can rearrange this as a thing. P is less than nu squared over alpha. You plug this in, the optimal value is this. If t bigger than nu squared over alpha, you plug that one in, and this would be the result. And it's just, yeah, so you have to plug it 1 over alpha here. That would produce the plug 1 over alpha. This. And then I do an inequality to simplify. So this is good enough if you just go with this. So then I'm going to simplify here. Because t is bigger than nu squared over alpha. You can see that this is basically nu times nu squared over 2 alpha. Sorry. Yeah, nu squared over 2 alpha, and then there's 1 over alpha that I take out. And I'm going to bound this part by, this is bounded by, it's actually bigger than, so this is less than or equal to t over alpha. This t is bigger than squared over alpha, t over 2 alpha. So, okay. And then you combine t over 2 alpha positive minus t over alpha, you get negative 2 alpha. And then you can see easily that factor 1 minus alpha here, or the boundary is the maximum of the two. This line is switch. You look at this, both of them at this value we give you the same value. So if I plug t equal nu squared over alpha, I get negative nu squared over 2 alpha squared, and so they have the same value at this point, and one of them is linear, one of them is quadratic. So it's just the situation that we have here. So a quadratic meets a linear function at a single point. So below it, the quadratic is dominant. Above it is the linear is quadratic the minimum. So you just can verify that this function can be written like this: maximum of the two, or if you factor out the negative 1/2, will be negative 1/2 minimum of it. You don't have to worry about this. Writing it like this. You can write it like this as well if you want. But this is a little bit cleaner. So that's the end of the story, because that's the minimum, and exponential is monotone, so it would be exponential of the minimum, which is so this would be like x f lambda star, and f lambda star is this. It's just the same idea. You have to be careful about the boundary condition. And you can also see, because we couldn't go all the way, we are not getting the tail that we could have had we had it for all lambda. Okay. So that's the result. Good. Everyone happy? So once we have it again, we can basically apply this to sums of independent subgaussians. The first thing that we have to show is that sums of independent subgaussians is again, sorry, so exponential random variables is again sub-exponential, and you carry in the alpha and mu that I get, and then I would have a result like this. And again, this can be replaced with negative x can be replaced with negative x, and balance the whole. So I can get a two-sided dot. that. So this is the next step. If xi are independent, then 0 means some exponential random variables with parameters ui and alpha I. If you let u be basically like the algebra with the u vector, sum of u minus square root, and alpha being the maximum alpha I, then the sum would be sub-exponential with these parameters mu and alpha, and then you have this parameter, which is so the only thing that you have to show is this statement here. To show that, you just write down the MGF bound that we have for each one of them. And we have it for, let's say, 1 over alpha I, lambda less than 1 over alpha I, for each of these guys. And these are nested intervals, right? So there are intervals around. So for example, I could have like 0. One of them is negative 1 over alpha here. The other one could be like negative 1 over alpha 2. 1 over alpha 2 here. The other would be like here. So the smallest interval that contains all of them would be basically maximum I of lambda is less than 1 over maximum alpha I, then this is less than 1 over alpha I for all alpha I. So I have all these inequalities in this the smallest of all intervals. So this is less than or equal to 1 over alpha I for all I. So on this little small interval, all of these inequalities, and then the rest is exactly the technology of MGF, basically. So e to the lambda Sn is the product of the MGF, basically. The product of these just get the summation. And so this part is exactly the same as the subjection argument. The only thing is that now have this, and you can see this is by definition nu squared, and this equality holds for this range. And if I call this alpha, this is exactly the definition that I have. So we managed to show that the MGF of Sn has this quadratic e to the quadratic form over this interval. So it has to be some exponential with those parameters. Then we apply all tail bound. So this just follows from the previous result. Okay. So this was a very nice tail bound for sums of independent. 0 means of exponentials. Of course, if they're not 0 mean, you can just apply it to xi minus the expectation of xi. Because this is what would have the properties that we talked about. So all these you can just apply the standard modifications. So the summation of this, and also you can get the double or two-sided version if you put a 2 here. Okay, all of these would work. And this is sometimes called Bernstein inequality for Bernstein inequality for sub-exponential random variables. There are a couple of inequalities traditionally called Bernstein. You'll see one in your hard problem, which is more traditional. It's like an upgrade of the Hoffman inequality in a sense, where your variance is controlled. Although here it's not an upgrade, it's just a downgrade basically, because you have slower decay tail. It's just like a more modern version of the Bernstein for sub-exponentials. The actual Bernstein is very useful itself, so you'll see there are 2 versions also. Any questions? We'll say this is going to be very useful for driving interesting results. Okay. It's fairly, I guess, straightforward. So if you're in characterizations, we have set of equivalent characterizations similar to the some Gaussians. But I've changed the slides a little bit. I removed, there were four. I removed one of them, which is not that relevant to us. So now we have four for this and four for the sub Gaussian case. So the first one is that the random variable is exponential. We have in some exponential case for some count constant k1. The moments behave like this for all p. So for the sub-Gaussian case, we had a root p here, so the moments grow slower. This grows like p, and this constant again is related to this constant with up to numerical universal constants basically. The next characteristic is that MGF of the absolute value of x is bounded at some point. For the Gaussian, sub-Gaussian, we had this x squared. So that was a stronger condition. This is the absolute value. And let's see. And the last one is the expectation of x is 0. The last one is what we had before. So you have the MGF has this quadratic upper bound, x to the quadratic upper for some lambda neighborhood of 0. You can see the constants here are the same, so that's the version that's in HTTP. Sometimes it doesn't matter, so you can. So we have nu here, nu squared here, and alpha here. So you can always take the maximum of the two, or like maximum of nu squared and alpha, and call it k5 or some k. Sometimes it's useful to have different parameters, especially, for example, in the case of the sum that we saw. For example, the sum, you would scale it that all the nu's are the same, all the alphas are the same. This is going to stay like root n times u, whereas this is going to just be the same alpha. So then this would not be a sharp thing to do. However, the way that people write it, or the HTTP writes this, they have like a single variable in mind. In that case, nu and alpha are just constant multiples of each other, so it doesn't make much difference to just keep track of one constant. Just have this in mind that, like in contrast with the sub-Gaussian case, there is some value in keeping these two parameters sometimes. But if you're careful, you're like, I know what you're doing, you can get away with this as well, get good bounds. So as long as you don't apply some of the things, for example. Okay. So this characterization in particular tells you, because it's absolute value, it's just, I believe it's equivalent to saying that the MGF itself is finite in the neighborhood of 0. Because if I say, if I can have e to the so imagine expectation of e to the epsilon x is finite, and then the expectation of e to the plus epsilon x is finite, then I can say the expectation of e to the epsilon, this is going to be finite. Because this is going to be bounded by the sum of the two. And so this is saying, let's say, I can have an interval around 0 that contains this. If I'm finite in the neighborhood of 0, the MGF is finite. This is the MGF basically evaluated at minus epsilon. So if the MGF is finite in the neighborhood of 0, I can have something like that, and I get like something like this, and so I'm satisfying this at 15 for which is 1 over epsilon. So this characterization tree suggests that any random variable whose MGF is finite in the neighborhood of 0 is going to be sub-exponential, which is a very general sort of statement. The things that are not sub-exponential are the things whose MGF basically like collapses to 0. So at 0, everything has like finite because it's like this. At 0, lambda equal to 0, this is always going to be 1. But I can move away from 0, or I can move to one side, but not the other side. Okay. If I have two-sided, I have a full interval around 0 that I can move around, and G is finite, and your demonstration. There's a pretty large class. A lot of things that usually people work with are like this. Again, some heavier tail things are not in this. For example, you can see that all the moments exist. So any random variable whose moments sort of go to infinity at some point, like for some p, the moment do not exist anymore. Like F distribution and T distribution for sufficiently large. Like in certain cases, then it wouldn't. I believe P and F is violating this in general, but heavy tail distributions for which the moments do not exist are not in this class. Okay, that's a pretty good class, pretty general class. Yeah, this is just comparing with the equivalent characterization. So there you have t squared here, root p here, square here, and this was for all lambda. For sub-exponential, this is t, this is p, this is absolute value of x, this is lambda in the neighborhood. 0. Questions? Okay, so this one again can be used to define a norm, just like we did for sub-Gaussian variables. The smallest k that satisfies this we define as a sub exponential norm. So psi 1. The smallest k for which this is going. And x would be sub-exponential if and only if this norm is finite. This is again a proper norm on the space of sub-exponential random variables, make basically the Banach space. And again, the situation goes like this: L infinity is in sub-Gaussian, sub-Gaussian is in sub-exponential, and then sub-exponential is in any LP, basically L3, L2, L1, and this is inside all the random variables, let's say. So it's a bigger class between sub-Gaussian and smaller than the equation to all. Okay. And then you can write all these characterization again in terms of the norm. Psi 1 norm, all these constants that we had there are upgraded to a constant or a constant multiple of their Psi 1 norm. So you can write these statements. So it's going on here, and I'm not going to spend too much time on it. It's just if you have questions, let me know. We have a couple of interesting results. The random variables of Gaussian can only be x squared is sub-exponential. And in fact, you have the psi 1 norm of x squared is equal to psi 2 norm of x squared. Okay, so this immediately says if x is sub-exponential, this side is going to be finite. So this side is finite, so x squared has. So this is saying x psi 2 finite implies x squared psi 1 finite. Okay. So this is just saying that's exactly what the x of that and x squared sub-exponential. The proof of this is exactly follows like not exactly, it's immediate from the definition, and I leave it to you. If you just compare the definitions, psi 1 norm and psi 2 has x squared here. You recurve it as p squared, and then convince yourself that smallest t that satisfies this and the smallest t that satisfies the other one of them has to be square root of the other. It's sort of rather straightforward. The next lemma is also interesting. So if x and y are some Gaussian, then the product is like some function. And this is a strict generalization of this. And the interesting thing is that x and y are not necessarily independent. So the lemma 2 follows from lemma 3 if I take y to be x. The products of sub-Gaussians are general so exponential. In fact, we have this called product of psi 1. No, psi 1 or product of psi 1. The proof goes like this. Assume that the psi 2 norms are equal to 1 without loss of generalities. Without loss of generality. So why can I, without loss of generality, assume this? Just see if you guys are following. So these are norms. Right? Yeah, go ahead. Yeah, great. So these are like norms are homogeneous. Right? So if I scale out x by alpha, alpha comes out of this as well, and I can cancel. So I can scale x and y by any positive factor. And so I can make them like divide basically x by the cycle of x. And y by the cycle of y. It just follows from the property of the norm. Okay. So what we want is this is like that, and I want to show that xy psi 1 is bounded by 1. And this is an instance of the Young's inequality. So Young's inequality says a b less than b squared over 2. Of course, this is like from high school algebra as well. So you can rearrange this to minus b squared. Positive, but it's like a very special case of the Young's inequality. It's just more fun to call it. We have this as applied to basically a equal x or absolute value of x. So take a to be absolute value of x, b the absolute value of y, and you can see I get this inequality. Then we have this, which is just the property of exponential, and then we have this. So why do I have this one? This is another application of this. So now A is this, B is that. Okay. And then by definition, this is less than or equal to 2. Why? One. Yes. Okay. So psi, if you remember the definition of psi 2, norm of x psi 2, this is n t e to the x squared divided by t less than or equal to 2, the smallest. So if I have norm of this being 1, it means that I should have e to the x squared divided by 2, or say divided by 1, less than or equal to 2. Okay. Same for y, and we have it less than 2. Now that I have this, then it follows this is less than or equal to 2. Now it follows just like 1 though. If I divide this by 1, it's less than or equal to 2, so the psi 1 norm has to be less than 1, because 1 sort of satisfies this. if this holds for some t, then the psi2 norm has to be less, psi1 norm has to be less than t, right? And holds with 1 here. And so the psi1 norm is less than. It's a very clean proof. And it's a very useful result because when you try to compute, for example, the sample covariance matrix out of IID data, multiplying a matrix by its transpose and produce these kind of terms. Very useful to know that products of sub-Gaussians or sub-exponential. Okay, sounds good. Questions? So this allows you to do a lot of manipulations, and by the fact that psi1 is both psi1 and psi2 are norms, and by these properties you can sort of do a lot of things. And there's also a centering lemma as well, which I'm skipping, similar to the centering lemma that we had for the psi random variables, or so Gaussian random variable. If you want to see a precise statement, see the FTP. So now we can restate Bernstein's inequality. If you recall, let's go back. This is if I want to replace this with, this would be summation y squared over I, and this is max alpha I. Both alpha and mu are upper constants bounded by the psi1 norm. Okay, so I can just replace both of them if I want by the psi1 norm here. I get max the psi1 norm and square the psi1 norm. This is another clean version of the Bernstein without, and then there's a constant unspecified universal constant. So this is very useful, and in particular, for example, if the psi1 norm of one of these random variables done by k, I can just replace. This would be. You can see that this bound is increasing in the denominator. There's like a negative sign and one over something, cancel each other in a sense. So if I make this bigger, I get an upper bound. If I make this bigger as well, so I'm going to replace them with summation, basically k squared, which gives me nk squared here, and this just gives me k. And then we have to do a little bit of work here. So what else I'm going to do is I'm going to multiply by 1 over n here. Let me do it elsewhere because this is useful. So so these it's good to just get comfortable with this type of argument. So first I'm going to write it like this: divide both sides by t, by 1 over n. So this is t over n. It's going to be less than or equal to 2x negative c min t squared over nk squared, and this is going to be t k. Okay, and then replace or change a variable. Do a change of variable because I don't want to introduce a new variable name. Just change t to n times t. This holds for all t. It certainly holds for nt. It's here. T goes to nt. Right. If I do that, this will become c. So I get probability 1 over. I put 1 over n there as well. 1 over n summation xi, I from 1 to n, less than or equal to 2x negative c min. I get the n squared t squared here, nk squared, and I get nt over k. Okay, and then magically one of these twos cancel with this n. Okay, and then I have a common n here. I pull it out, So this would be 2x negative c n here, and then min t squared over k squared and t over k. So this is a clean form, and you can see that it's exponential again. So as the number of terms grow, this goes down like into the negative sum. Constant times n. So assume the t is constant. This would be constant. So it has a similar feel to the exponential, sub-Gaussian case in terms of the dependence on n. So the average concentrates around its mean, which is 0. And if things are not 0 mean, then you just apply it to the center version. Okay. So these are all restatements of the Bernstein inequality. You can see we got it for very, let's say, cheap price. So it's a very powerful inequality, but we didn't do much work for it. We just did it for a single variable, then concluded that the same thing holds for the sum, and then maybe a little bit of the fact that this psi 1 norm is related to that. Actually, we skipped the proof of the equivalence, but that's also a straightforward step that the psi 1 norm is in 1-to-1, not 1-to-1, but can be replaced, or you can replace nu and alpha with the psi 1. But when you get these powerful inequalities and they apply to any distributions for which the MGF is finite and negative 0. So this is sort of a like an endpoint that one wants to do. One have exponential concentration inequalities for some of the independent random variables, and this is a very good section for it. Okay. Questions? For example, you can use something like this to derive concentration inequalities for chi-squared random variables, because you know that a single Gaussian, if I square it, it's sub-exponential. If I add a bunch of independent guys like this, like chi-squared 1, basically the chi-squared n degrees of freedom. So chi-squared n degrees of freedom is just the sum of a bunch of sub-exponential. So this inequality gives you a concentration inequality for chi-squared random variables. These have been studied like previously separately. You have the PDF, you have the tails, you can try to analyze them, but this general machinery gives you a very sharp tail, which is good enough. Actually, here I'm using the other characterization with the 2 parameters. So if you have, because you have calculated this parameters, yes, but you get explicit constants here, which is useful. If you use the other characterization, it's just that the I squared are sub-exponential with nor psi. You can do it like this. So you can say psi zi squared psi 1 norm is equal to zi psi 2 norm squared, and zi psi 2 norm is just a sub-Gaussian norm of a standard norm, which is a number. And so this is going to be bounded by a constant. So you can say less than or equal to 1 up to a constant. And then if you write down the Bernstein, it would be negative c min t squared and t. So this is the k here that we use. K would be 1, let's say less than or equal to 1, up to a constant. I can absorb the constant into, if I have a bound on this, but up to a constant, I can pull out the constant. You can justify for yourself that I get a different constant here. So if you don't worry about constants, basically you can say that this is 2 negative x minus c times min t squared and t. So this argument gives you a very immediate bound. without even needing to calculate these things. You just use that fact and the fact that zi subtraction normal is calculating with a number. Standard normal. There's no parameter there. And so it immediately gives you a bound like this. If you use these parameters from that inequality, you get a bound like that, or for the average. So this is the average. I have to subtract the mean. The mean is 1. Subtract the inside the sum, outside the sum, the average. So you get in the end this product. It's straightforward application of either this inequality. So here we're using this version, right, with each one of the nus being 2, each one of the alphas being 4. But if you don't care about the constants, you can also get something like that rather quickly. Is it sort of clear to people? What I'm doing is like I'm applying that thing with nu I squared being equal to 4 and alpha being equal to 4. If you do it with the first thing that we had, you get something like that, and then you replace should be bigger than t. And then you replace t with nt, and then n comes out like we had. So it should be straightforward to draw either this version or this version yourself. I'm just going to skip the detailed steps. Just yeah.
I have a question about the effect n has here, because when n is too large, aren't they actually greater than
Sorry. Okay, right. I made a mistake. There is an n here as well. Oh, okay, so no, this is not what I want. You're right. So this is not the correct statement. So I should have said, let's say we're going to use this. Okay, so k is up to a constant like this. So I can just remove these. So the bound would be something like that. So if you want to use that approach, the bound that you get, this wasn't correct. So you get x negative c and min t squared and t. The only difference is that now I have an explicit set of constants. So the other approach gives you an unidentified constant. Yeah, thank you. So the n should be there. Yeah. Otherwise, this approach is used. Yeah, I understand. So what I'm doing here is just apply this with k equal a constant, which roughly you can say k is 1. Just inflate this constant. Okay. Questions? So this is the approach of the HDS book. This is what like the HDT would do if you wanted to get a concentration quality. Yeah, I actually did it here as well. So there is one step that I skipped. So if you want to do it properly, you have to bound the psi1 norm of this because we are applying this result to zi squared minus 1, okay? Because xi's are supposed to be 0 mean here, so these are 0 mean. So zi's are Gaussian, so we're working with the square, so the square is at 0. So I have to control the psi1. So the k that we have in that proposition is the psi1 bound in the psi1 norm of this. This is where we use the centering, which I skipped. So it's up to a constant bounded by the psi1 norm of the uncertain version. This is going to be equal to this, that we covered. And this has to be a c. So this is going to be a universal constant. And this is going to be a universal constant. And so the product would be another universal constant. So there is a step that we skipped, but then this is saying, this is my K basically. Okay, so I'm saying that Zi squared minus 1, psi 1 is less than or equal to C, so I can apply that result with K equal to C. That's exactly the result that we had, the Bernstein version there. And then I pull the C out, and then I get a C2 here. And this is the details if you're interested. You can show that if I take C2 to be C times the minimum of the two things, 1 over C squared and 1 over C. This is work. The minimum gives me the upper bound because there's a negative sign. So I'm going to replace these two with the minimum of the two, and I have the same thing and pull it out. Minus C, I get C2. So once you get comfortable, you do this in your head. You don't have to write this down. Just remove these and just do C2 here. So this is the second approach. I did it like, sort of harried way, did both, but this is the first approach using the two parameters. Let's say remove this here. And then the second approach is this, using the psi 1 norm. So from the other approach, we get explicit constants here. From this approach, we get the qualitative bound, just we don't know the constant, or we don't care about the constant. Sounds good? Maybe pause a little bit here. So one consequence, for example, is that if t is less than 1, you can see t less than 1, t squared will be dominant. Okay, so when t is less than 1, this behaves like a sub-Gaussian. So you have this sub-Gaussian type bound, which is what we're going to use next. So this is the inequality I'm going to use. Actually do something useful today. Questions? So if you have like questions, I encourage you to go through, try to prove it. Both versions, try to prove both versions yourself. It's a very good application of these ideas. So you know how to use these concentration inequalities. So, okay, so what I want to do, we start to do in the remaining time is to discuss an application of that concentration inequality for chi-squared random variables. So the topic is random projection for dimension reduction. And another way of saying it is this is about Johnson, Strauss, and Lemma. So what is the idea? The idea is that if I have a bunch of points, let's say deterministic points, U1 up to UN, these could be like images or other type of data in RD. And D is high dimensional, let's say. So you have a big image, you look at it as a matrix of pixels. Let's say if it's like MNIST, it's like 28 by 28 pixels, which I believe is like something like, so D would be 728. So that would be my D. So an image is like a vector, there's a vector in 700 dimensions. And then I have like a lot of them, let's say in the MNIST, like MNIST, it's like 60,000 something. You have this many images. And it could be smaller, it could be larger. What we want to do is that we want to compress the images or data to a lower dimension while keeping their similarity, basically. So later I can do like classification tasks or some other tasks. And their similarity, let's say we measure by pairwise distances. So if I pick UI and UJ, I take the distance. The distance would be a measure of similarity. Another thing is like the inner product. But let's say if I normalize all of them, the norms are equal, they are like unit norm. Then the square of it is 1 plus 1 minus 2 times the inner product. So the inner product and the Euclidean distance would be the same. If I preserve one, I preserve the other if they're normal ones. So let's say focus on this distance. We want to find a representation that's low dimensional, but has this pairwise distance preservation property. So what I'm going to do is that I'm going to basically, the general idea of dimension reduction, or let's say representation, if you're deep learning people, it's like I want to apply a function f ui such that if you apply a function or find a function such that when I apply it to these data points, this is approximately close to ui minus uj. Okay, so I want to find a representation where, let's say, this f maps from r to the d to some r to the m, where m is much smaller than d whole cube. So if you have seen like these deep learning architectures, there's like an encoder. You have the d-dimensional thing comes in, you reduce it to like an m-dimensional thing here by a neural net, which is a nonlinear transformation, and then the same thing goes back. The decoder comes in, takes it, and pushes it back to R to D. So we don't care about this reconstruction at this point. We care about this representation such that in this domain, the distances are preserved. And the interesting fact from the high-dimensional probability idea is that this can be done by the linear transformation. You don't need nonlinear transformation. Nonlinear transformations are interesting, but even if I do a linear transformation, as long as it's random, so if I take f of u to be xu, where x is a matrix with random entries, oftentimes I can achieve a very good reduction. So that was the idea of Johnson and Strauss embedding. So we take x to be a matrix, or you can think of a matrix as a map, linear map from Rd to Rn, which can be represented as a matrix f by d. You can think of it as a projection as well. You can try to find projection matrices. But what we're going to do is that we're going to look at a random matrix which acts like a projection matrix. It's close to a projection. Not a projection matrix, but one half of a projection matrix. So what we're going to take is take x to be 1 over root mz. Okay, z is a matrix whose entries are IID standard norm. It's a simple thing. Just generate a matrix m by d, fill all the entries with standard normals IID, and then rescale 1 over root m. Okay, so the matrix is something like that. M small, d big, and then we rescale by 1 over root m. The effect of a scaling by 1 over root m is that we'll see that the L2 norm of each column is roughly 1. So this is like the standardization. It's not exactly 1, but hopefully by the next few lectures, you're convinced that it's very close to 1. If I had a Gaussian vector, IID entries, standard Gaussian vector, IID entries, m-dimensional, if I divide by 1 over root m, the norm would be very close to 1. So that's what this is doing. So that's x, and then I'm going to apply x to each one of my data points. The result is that the pairwise differences of the squared are within a factor of 1 plus delta and 1 minus delta of the original distances for all pairs of I and j. So we preserve, it's the key is that we preserve all pairwise distances on these points. Not like over the entire space, but given the points that you have. So all the pairwise distances that you can care about where n choose 2 of them. So n choose 2. So the result is that we have this equality 1 minus epsilon if we take m. So the only parameter that we specify is m. If we take m large enough, and this is enough. Okay, so we have 2 things here: delta, which is the stack, the equalities here, epsilon, which is the stack see how it is here. So n even is 16 or number squared log n. That's all. So the very interesting thing about this classical result is that the dependence on n is logarithmic. Have a lot of points. This is not going to grow as fast. If I double the number of points, I'm just going to add like a factor of log plus a log 2 factor. And so often, like from a asymptotic perspective, this is very interesting because this d could be very large, and this doesn't appear here. The ambient dimension doesn't appear here. The only thing that sort of matters is the number of points and also logarithm. The thing that sort of flows about this is still it's unavoidable. But let's say if I have 1/2 here, up to like I would do 1/2 here, 3 over 2 here, and this is like 4. This is 4. Yeah. 64 log this. It's pretty big, but let's say this is like 1,000. 64 is not big enough. It's not good enough. Right? If this is like 10,000, let it be like 0.1. The key is that this is not 0. So it's like sandwich between. Yes.
I don't understand here is that so it doesn't depend on D, right?
Yes.
So basically there is no difference for the error we are like let's say we have some epsilon and delta and and for one set of data D is equals to 3 and for another 3,000.
Yes.
But for both of them because n and epsilon and delta are the same, the n will be equal, but it doesn't make sense.
So this is a probabilistic statement. If D is very small, this might not be very useful. Because the bound is quite like the n is bigger than the ambient dimension.
And will be basically equal to 3 on the left.
Yeah, so this is again here this is useful if the n that you get is smaller than D or much smaller than D. And it's just that I should say it's a probabilistic statement. It's not saying that you preserve this always, like for all of them. Preserve a certain probability. So this would be like point interesting here. So I can take 0.01, so 0.99 probability. Oh, that's actually like very small as well, because it's inside the log. It's not intuitive, I agree. So it's not intuitive, but once we go through the proof, hopefully you're convinced that this should hold. The thing is, even if you're in the ambient dimension, I can give you the intuition. So they could be all on a line, although they're sort of in the d-dimensional space. The actual space on which they lie might be one-dimensional. Okay, or it could be like three-dimensional, right? This is saying that basically any bunch of like endpoints that you look at. They're not going to lie in a high-dimensional space. They're not going to lie, like they're not full-dimensional. They're going to lie basically close to something like that. It's a very non-intuitive fact, and it's just part of the surprise, I would say, of high-dimensional analysis, like high-dimensional concentration of measure. So they're saying you have some points. They're roughly like geometrically as if they are. Okay, with this how probability they look like that. But let's go through the proofs and we'll come back if you're not convinced, then we can check.
Or like you can think of it as even though like the points technically not in the space, we really only care about like the full and square distances, pairwise distances between points.
Or yeah, but then n could be even larger.
Oh.
Yeah, this is like in this example that I had even like you see n is much larger than this. Yeah, so the thing is that
yeah, like that's why I first thought that.
Sorry?
That's why
It's independent dimension, yeah, so you care, yeah, exactly. So you care about this, so it certainly depends on M, which is good news. If it's just independent of both B and M, then it would be very bad. But the thing is that it depends on the number of distances that we want to preserve. That's correct. The fact is that it depends on it in a log fashion, or n squared, but the dimension is not going to go like n squared. It's going to go like log.
if you have like dimensions, because if we're like this is random, if we're taking the question this is random, then if we have two dimensions, then there are like two infinity things that we can store.
Yeah.
So that would explain a lot.
Okay, so you're saying this is it's going to get bad when this is close to 2 to the d. Is that or
If you have, I mean, so that's like Lorentz for connection, so it's not exponential. And if you have like, if you have n independent channels, then it's more exponential with respect to the number of channels you have, right?
if you have n
Like if you have like n bits, let's say, you can store 2D things on those bits.
okay.
So here you have m dimensions, and the things that you're storing are pairwise distances between points.
Right. Okay. So you're saying you're storing to the n amount of information that can
You have like all of it.
n squared. Okay. Yeah. Okay. That's a good analogy. I like it. Yeah. Maybe we can come back once we go through the proof. Maybe you can just restate your statement, see if you can connect with that. Okay. Thank you. See you next time.